Okay, we move on to another section, still under mechanical properties. Just now we are all on the parameter, individual parameter, stress, strain, shear. Now we try to link into graph in the graph form, where you will see in the industry. When you go to work, you will see this graph if you deal with material. Okay. So we will derive or estimate or evaluate the properties of the material using a test called tensile test. This will be the machine. Currently, we are getting at least 2 tensile machine for you guys. One is on the way from China. Another one still in procurement, still in ordering, still in negotiation. Currently, we don't have this kind of machine yet. We have the very traditional one, use hand one that you'll see in your lab. Okay, so it looks something like this. So you have a 2 arm that's pulling the object. Everything is automation. You click on the computer or touchscreen, then the thing will do all the things for you. Okay, you can set how fast you want to pull, and there's a sensor, load sensor there that give you the stress. Then the auto convert into stress for you. Okay, so this is the old one, not old one, but this setting is for like concrete bar. You need this setting because the 2 column here maybe cannot support the pulling force. So you need something like this to pull a stronger material, like 2 pillar. If you take out this cover, also you'll see something like this, but the design a bit different. Okay. So in the experiment, you also see, we'll give you a sample like this. It's called tensile sample. So different you have a different type of sample. One is rectangular. When you do this test, you have different standard. If you test plastic, you have a certain shape of sample. If you test metal, you have a different sample. So this one, you have a round grip with the round sample body. Okay, with the round sample area here. Standard already. You fix the length already, so that everyone, when you do tests around the world, you can do comparison because you are comparing the same dimension of the sample. So you can make comparison. So yeah, so you apply for the same for other experiment that you need to do for other module. When you conduct experiment and you need to do comparison, you need to fix some parameter. For example, you fix the shape of the sample. Then by changing the material, then you test, then you can do comparison. If you're changing the dimension and then you test, it's like you're comparing apple to orange already. So you're not able to make a very sound, very good comparison results. Okay, so this one you can refer to standard in testing material. They already lay out already how you prepare the sample. This one also link back to your technical drawing lah. If you're taking technical drawing, how you draw the hidden line and all these things. Plus minus is the tolerance that you have. This tolerance is important in engineering drawing and also in engineering production. When you go out later, please pay attention to the tolerance here. This tolerance, it can cost you some money if you're not careful, because the more decimal place, you need a better, powerful machine, because you need to cut more accurate in the process. For example, your phone casing, if you open up the button, all these things, they have a very high tolerance. If it's have a differences of 0.01, you're not able to fit in the button and all these things. Okay, back to this one. So this is another type of sample. Just now it's a round cylinder, this one. And there is a flat, the one. This one you see in the tutorial question just now. Okay, you see the same. The test section here is always 2 inch. The test section always 2 inch. Because according to a certain standard, you need to follow the exact length before you test. Okay. So what is tensile testing? So that let's just let you know how it behaves.
Tensile testing is a basic form of mechanical testing that can be performed on a universal testing machine or a dynamic fatigue testing system. A tensile test applies a tensile or pulling force to a material and measures its response to the stress. This enables engineers to assess the material's suitability for its intended application. Materials in all industries are commonly subjected to tensile forces. For example, the elasticity of tire rubber is critical to tire performance, while rebar is used in the construction of concrete structures due to its superior tensile strength. Other commonly tested materials include plastics, thin films, composites, metals, and textiles. Tensile testing is also performed on finished products, such as medical tubing and sutures. These devices are critical to patient safety, and their mechanical properties are strictly regulated by the FDA. Tensile tests are performed using a wide variety of grips, fixtures, and accessories designed to accommodate different materials and specimen shapes. While different standards require the measurement of different mechanical properties, the most common properties of interest are breaking force, modulus of elasticity, elongation or strain, and tensile strength. For more information on mechanical testing, subscribe to our YouTube channel.
We try to get this brand, but it depends on approval. Very expensive, but good one. Okay, so this will be the typical graph that you will see in the test, final exam. So you'll be seeing engineering stress versus engineering strength, and you're seeing a few dots over there. A few regions in the graph, a few regions in the graph. You have stress versus strain, and you'll see a line, straight line, and then curve. Identify the straight line. Straight line give you y equal to mx plus c. All the tests from 0, so your c 0. So this graph, y equal to mx. What is your y? Stress. What is your m? You write m and strain. Recall back, there's Hooke's law. Compare with Hooke's law. Your m is your modulus Young. This one happened in the straight line region. Okay. Law apply in the straight line region. It's called elastic region. Elastic region means you load the object, you let go the load, it still go back to original length. The area also will go back to original area. Okay. This is the region that we want to work at for all the application in engineering, because we don't want to fail the structure. Okay, this is an important properties. We want to remain in the elastic at all time. Because after this dot, this maximum point, it can still hold some load, but it will going to fail at a certain point. The point passing the maximum dot of the straight line is called plastic region. Plastic region will be like bubble gum. You pull, stay there, pull, stay there, pull, stay there. The length will stay there. Okay, the length will stay there. So it will show you some parabolic or quadratic equation kind of behavior. Important point for this curve is maximum point of the plastic region. And the last dot in the machine or in the test, this is called fail point of already fracture. You broken already, no data collected. Maximum here is, we call it UTC or UT, ultimate tensile value or ultimate tensile something. UT something, you can call it UTC or UT something, ultimate tensile point. We don't want to load our sample up to this point. This point will be used for design, for example, bridge design or lift cable, the lift elevator cable. So the lift cable, we don't want it fail, so we'll use this one and then divided by the safe factor. This don't want to go. After this point, after this maximum point, the material considered not useful anymore, because it's already reached the maximum length that it can go. Then after that, it will like bubblegum melting. It will auto elongate until it fails. Okay, so you can see here, there's a ultimate tensile strength, UTS, ultimate tensile strength, the maximum point you have on the curve. In this example is 87, or in this example is megapascal. Okay. This graph got two y-axis. If fully, don't read the wrong one. Left hand side is in, right hand side is in unit SI, megapascal. X-axis is in inch over inch, but doesn't matter. Strain is just a deformation value, doesn't matter. So this one can be mm over mm, is still same, also strain. Right. So just be careful when you do your test. Look carefully, don't use the wrong axis. You are using, for our standard in engineering program, we are using unit SI. So go and see megapascal axis. Don't read the imperial axis. This will be the careless mistakes. You straight away, you assume this one is unit SI, then wrong already. Okay. In application, in the real job, if you read the wrong side, you are trying to kill someone. The value is a bit different. Either you over design or you under design. Okay. The rest you read. Okay, the rest you read. Different material have different line. Okay, different material have different line. So on this graph, we're going to learn all these things. Modulus of elasticity, I already show you, is y equal to ms plus c, is a radian of the line. And we're going to go into this. How we know the maximum point is stuck to plastics. How we know? Or we don't use the wrong value in our calculation. Here, 2% offset. Okay, I just give you the info first before we go into the slides. So I enlarge the graph. Okay, let's say you get an experiment like that, right? You get an experiment value like that, and you want to estimate where is the plastic start to happen. Okay, you can use a ruler to join all the dot here, but this is not accurate. Right? This is not accurate. So we'll use a certain percentage. Some country they use 0.2%. Some country they use 0.1%. What does the 0.2% means? It go to the strain here. and it multiplies. So 0.2% equal what value? Decimal place? 0.002. Correct. Correct, right? 0.2% you convert into decimal place is 0.002. You know that strain, how to calculate strain, right? So strain also give you a decimal place. So what you do, you go to the bottom of the chart, you go and find 0.02, 0.002. If you are using 0.2% analysis, then you use your ruler, put on the elastic line, push toward the 0.002 line, draw a parallel line, draw a parallel line along this one. Okay, my drawing a bit bad lah. The intersect of the dot on the curve, this value will use as value for plastic start to happen. This value you project to the left, you get one value stress. This is, we call it start to have plastic or sigma plastics. It start to behave or showing behavior of plastic. Means no return line, no return point. You reach the maximum that it can go. After this dot, it start to continue to stay at that shape already. Okay, so this is 2% analysis. It can be 0.1%. It can be 0.05, 0.001%. It depends on the accuracy of that data. If you go to nano structure or nano material, then further lah, this one will go further down the value. Okay. Ultimate tensile strength, already explained. The third item, UTS, is the maximum dot on the graph, or maximum point of the graph. Okay, how to find maximum point by mathematics? You know, at a curve, you learn about dy dx. You have a curve that if you plot experiment, you can pull in the trend line. You will get ax squared plus bx plus c. Or it can be parabolic, it can be ln or something. But anyway, whatever the form of the equation, when you do dy dx, mean you're calculating the gradient or maximum point. So you know that at curve, maximum point dy dx equals 0. This is where you find the maximum point on the curve. So you'll be given from the experiment analysis, you're getting a curve. So you can use the Excel to call out the equation for you. Then you use some software or online platform, calculate dy dx, or to find the dy dx along this curve. Ask the computer to detect where is the dy dx. Then it pinpoint the dot for you. Okay. All right. So this will be the how you use in the industry. I won't ask you in test. Just let you know. Percentage of elongation in fracture, you know lah. Percentage of elongation is actually you take the strain, lateral longitudinal strain, multiply by 100%. You are pulling longitudinal ma. Okay. Don't confuse with the lateral. In normal application, we only focus on longitudinal. When you do analysis, when you see Poisson ratio, then only you consider lateral. Percentage of reduction of area, fraction, this one focus on area, also linked with the Poisson ratio. Area is lateral direction. Modulus of resilience, that one I'll show you the graph. I'll show you the slides. Toughness, and so on. So we are covering most of the info already. Modulus of elasticity, basically you return to the original length and it apply Hooke's law. This already explained. This is just information for you. Okay, unit of modulus Young will be the same as stress because strain don't have unit. Because strain don't have unit, so we carry the stress unit. Okay, this one they explain. Okay, U strength. U strength is where it start to show plastic deformation. It's very hard to find the U strength point. We use, in this case, we use 0.2% to estimate the U point, or you will see in the material handbook, you will see sigma Y. It means U point. U means it start to behave like plastic already. Okay. Or you see the question in the test. Identify from the graph the U strength value by using 0.2% analysis. Means you go to the graph, you identify if 0.2%, you identify 0.02 mark point, then you draw a line. Okay. So here is how I show on the whiteboard just now. If you are applying 0.2% plastic strain analysis, so 0.2% is about 0.2 offset. This one 0.2 offset is 0.02. So you go to 0.02 point. So this is 0.2% offset. You convert the percentage into this value. All right. So you get 0.02. Use your ruler, draw a parallel line. You reach a point up there, which is about here. About here. Okay. Why? Because in real case, the curve here is very difficult to identify. It happened very, very fast. It happened very fast. So it's very hard to identify. So we use just an estimation method, 2% to estimate. Okay. So this is aluminum. Okay. So the rest you read lah. If you understand, then can go. So it will yield about PSI, but again, on the left is imperial unit. You need to extend to the right hand side. So it's about 500 something megapascal. Okay. This is a note. If you work in UK, they use 0.1%. What means by 0.1%? Same. You shift to 0.001. Draw another line. Means 0.1% means you accept a lower plastic value or U value in your design. Means you'll be more conservative in your design. Means your design will be you're very conservative lah. Very conservative, and you're confident in the strength. You're confident in your products. Okay, this one I just tell you lah. Elastic and plastic region lah. So P point is maybe it happened at P point, but we estimate at 2%. We estimate at here, U point. Okay. So in experiment, don't use the first dot and the last dot here. You can use maybe the last 3 dot and the first 3 dot, then you connect, then you find the U. Don't straight away use the last 2 lines. Okay. UTS, ultimate strength, basically you label as sigma U to represent ultimate. Is a maximum point on the curve. Okay, so this is to make sure, is to know which metal is stronger. which metal is stronger. But this value is you won't use this value in your design, in your material selection for your design. You will use the yield value, this value, the 2% expansion. Because this one is, it already failed already, so it's not meaning, no value in your design. Okay. However, you see this one value in the catalog of material producer, because this value is higher than the U point. For those people that not good in material engineering, they might think that, oh, your product is better than another company. Even the different brochure, but one it give you the U value, one give you the UTS value. So by comparison, or you think that, oh, this one is higher is good, but actually you are reading the wrong things. It depends on application. Because on brochure, on catalog, they want to sell you something. Of course, they will use a more better value lah. So when you read carefully, they will give you UTS value, they will give you U value. But as a design engineer, you don't want to use UTS. Or UTS is your minimum or maximum value that you can go, because maybe you are the boss, you want to control costs, that is the value that you cannot negotiate anymore, because after this you're going to hurt someone, your product going to explode. If you're designing the propane gas tank, try not to use this one. You're going to kill someone. Right? Okay, so for ductile material, you'll see this behavior is called necking. You'll see this one in the experiment later. So this one, you will see this one already means it already reached the UTS point already. After this, it will snap already. Okay. Okay, the rest you read. So this is the illustration of the point on the line. So sometimes the question will give you 3 marks, ask you to draw what happened to the tensile sample. Just 3 marks. This one only happen in test. It won't happen in final. So this one, it will just return to original shape. This one start to become thinner. And after the end point, the maximum tensile strength, it will show necking. This one is a failure already, start to break. Okay, so if you compare the behavior of line between two material, if you see the steeper line, the material showing you steeper line and break at a higher point, it means the material is brittle, showing brittle behavior. It's like glass, or cannot use glass, titanium, all these things, or carbon steels. They will break at higher value, but very short strain. Means it's more brittle. Then if the material can drag very long one, drag, that means the point for the strain is the deformation. So you have a longer line of deformation, means it's a ductile material. So in your report, you need to mention brittle and ductile. Which one is more brittle? Which one is more ductile? I'll mention these two things. And you will see this one in test also. Describe which material is more ductile from your selection. Percentage of elongation, you just calculate from the calculation. And this is a tensile machine. You have devices here crammed to that sample. This devices is called elastometer. 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 You're actually detecting the elongation of the sample. But nowadays, they upgrade the machine. Some of them, they not even need an elastometer anymore, because they already install sensor in the arm here. So elongation, you already learn how to find percentile of elongation, which is the strain. And you have seen this one before, yield strength, tensile strength, ductile. Okay, so when you need to use yield strength, when you need to use tensile strength, and ductility is percentage. Ductility is percentage of elongation, which is percentage of strain, longitudinal strain. Okay, tensile strength is UTS. Is the maximum point on the curve. Yield strength is the one that start to behave plastics. So these are the properties of different, these are same ion in different temperature. So you see the curve, green line at room temperature is more ductile, but it behave like brittle when you cool it down, become negative, it become more brittle. So play around these two word lah, brittle and ductile. Okay, brittle and ductile. Okay, ductility, how you describe ductility of the metal? You use reduction of area or strain, actually it's a strain percentage, and we use area. Or you see the question mentioned ductility already, you need to calculate the area already. Just give you hints. You see that the question mentioned ductility of metal, something, something. In your solution, we expect to see area calculation. Okay. Some question, they will use calculate the index of quality, bracket ductility, percentage of reduction in area in question. The rest you read, the rest you read. Okay, this example 7 is just application of what you learned. So it asks you to calculate percentage reduction of area. Basically, you're taking area, compare the percentage of area. Okay, this one you go home and see. Nothing complex. This is just for show. You don't need to take this one, you just calculate. Um, uh, Again, your question? Yes. Yes.
So you get like a positive answer. So what if you do modulus of final minus initial to get rid of the negative? Is it acceptable or?
Let me see. Yeah, previous example, we always use final minus initial. So in this case, we take initial minus area, percentage. In this one, tensile. Okay, for area, we take initial minus final for area. For length, we take final minus initial under tensile loading. You mean this one? You mean this one, right?
Yeah.
You flip the thing. Oh, means you put like this. Okay. Yeah, you can actually, you can. In our class, I accept. If you flip final minus minus initial. Important is you compare to the original lah. Because this one is just to calculate the differences. Okay, you can put modulus in this reduction percentage of reduction in area, you can. Okay. You'll get 53% for this question. Okay. Okay, a little bit more. Modulus of resilience. What is this? Is linked with the energy absorbed by the materials when you pull or compress, or UR. This UR usually due to a scenario where it prior to yielding this point. When you do analysis, prior you reach this one, you are calculating the modulus. So what is this modulus of resilience? Is area under the graph, under the linear elastic portion of graph. It means it's under the elastic region of the graph. This one. The E region. This one gives you the resilience. Resilience.
So when we say that the material is yielding, that means it's behaving in a plastic manner.
No, not yet. Here, prior to yielding.
Yeah, but like what yielding itself. That's mean
like yielding already plastic, already start. You can say already plastic, but this to calculate the resilience is before you start yielding. So it's safe. It's a safe way. You use the elastic line region to calculate. So on the graph, you know that this is straight line, and you pull down, you actually get the right angle triangular. So you can use the formula for calculation for triangular area, half base and height. Half base, what is your base? Is the strain value to the U, and multiply by the height. Height is your stress U. Pay attention to the Y, sub Y here. Sub Y here, by using, let's say, 2% analysis, you need to find the dot, the point for the U point on the graph. Not the last point of the elongation. You need to go and find the U point on the graph by 2%, let's say 2% analysis. Yeah. So usually this question, you need to attach together the graph and submit. You need to do something on the graph. You do not attach means you lose many marks in the marking. This graph alone, if you show how to do percentage, 2% percentage, at least 5 marks there. At least 5 marks for the dot and the value that you show. So on the graph, remember to show all the dot line and all the intersection point. You need to extend to the left or right, depend on the value you're using. So if you this one, you're using megapascal, please extend to the right and write the numbers that you are estimating. Okay. The unit for resilience, because you're multiplying stress and strain, the value will be, because it's an area, it will be Newton meter over meter cube. You cancel, you get Newton over meter cube, also Pascal. So it can be in the volume form, it can be in the joule over meter cube. Do conversion, is either one of these also accepted for resilience. Newton over meter square. If the question asks you in volume, you start to see volume already. You modify this unit a little bit. You multiply the denominator with meter. You need to add meter on the top, so you get meter cube. And the top is Newton meter. What mean by Newton meter is the moment already. Means the torque, the Newton, or the moment already. You take moment divided by volume, means the twisting things. Then, or you can, Newton meter also means joule. You will learn this one in your coming static class. Force multiplied by distance traveled is a work done by the force, joule. Okay, the rest you read is about, if you understand this one, the rest is just elaboration. Okay, this is just extend what it means. You can put this equation in terms of stress. So you just multiply, change this strain into using Hooke's law, modify this one in the term of sigma. Then you arrive at half sigma square E, meaning you not even need a strain value to calculate for resilient. When you know the yield stress, you can straight away calculate the resilient energy or modulus. Okay, E you can from the table. Every type of material have the E value. This one from graph. To find this sigma Y, you need to do analysis 2%, 1%, depend. The orange color region. Yes, all of it. We assume it's a triangular. Just for a very quick analysis. Okay. Usually it won't be very much. So we just have a very quick analysis, triangular there. From here to here. So we get roughly the triangular there. Okay, roughly. The rest, you have class, right? Oh, class? No class. No class, huh? Let's see. Maybe we continue. Yeah, lah, we continue next class lah. We have 30 more slides, so we stop here.